Hello, welcome back. We have been looking at magnetism, and we saw that if we have a moving charge, that a moving charge will create a magnetic field. We used the Biot-Savart law to calculate what that magnetic field is due to a moving charge. Then we also used the Biot-Savart law to find out what that magnetic field would be due to a current in a wire. And we saw that we could use our right hand and point our finger in the direction of the current, our thumb in the direction of the current, and then our fingers will curl around in the direction of the magnetic field. Now what we're going to do is something similar to what we did with electric fields, where we found that if we used the symmetry of the electric field, that we could put a Gaussian surface around our charge and we could see what that flux was through that Gaussian surface. And that would tell us what the charge was inside our Gaussian surface, as long as we had a Gaussian surface, a closed surface. Now what we're going to do is do something similar with magnetic fields. And we're going to start first by looking at a line integral and reviewing a line integral, and that will help us develop something that's similar to Gauss's law. It's called Ampère's law. So let's start first by reviewing line integrals. So in the figure, we see a curved line that goes from an initial point I to a final point F. So here is our line from I to F, and it's curved. It's not straight, it's just a curved line. Now what we can do with this line is we can break it up into little tiny pieces. We can break it up into little tiny pieces, delta S. So the line can be divided into many small segments. And if we add up all these little segments, all these little delta S's, the length, that will give us the length of the line. So what we want to do is take all these little pieces, these little tiny pieces of delta S that we've got here, right here, all these little pieces of delta S. And if we take the sum of them over a number from, if we want to find what they are, we're going to do the line integral. And so the sum of all these little pieces over a number of them from 0 to k number of little piece segments of delta S, then we can say that as we get those delta S's really small, we can then call this an integral, and we know that integral is just the sum. So it's going to be the integral from I to F of ds. Now that's a line integral. So now let's take that line integral, this line right here, we're going to take this line, and let's put it inside a magnetic field. So now what we see here is we have that same curved line, and now it's passing through a magnetic field B, where the blue lines here are vector lines indicating the direction and strength of the magnetic field B. So now what we can do is we can take our line and we can again break it up into little tiny pieces, delta S. So we can break this into little tiny segments, delta S, where these are little vectors, delta S, the displacement in that over that little piece, delta S, along the line. And so if we want to find the line integral of, the magnetic field B from I to F as measured along this line in this direction that we have indicated here in our picture, then what we'll do is we will now take the sum of the pieces of B that are in the same direction as S. So that will be BK dot ds. So we're going to do the sum of BK dot delta S. And that will then just become the integral of B dot ds, where I want to remind you for the dot product is the magnitude of B times the magnitude of this little piece of ds times cosine of the angle between them. So let's look at what this means if we're looking at a line that's passing through a magnetic field. So here in our first example, from point I to point F, our magnetic field in this case is everywhere perpendicular. So we see that every single one of these vectors is perpendicular. is perpendicular to our line. And since it's perpendicular to our line, it's perpendicular to our path. And we know that B dot ds, as I just was saying, is the magnitude of B times the magnitude of ds times the cosine of the angle between them. And the cosine of 90 degrees is 0. So in this case, it's going to be the magnitude of the magnetic field will be 0. Now let's look at this example down here. Here is our same line segment going from I to F in that direction. And in this case, what we see is that the magnetic field is everywhere tangent to the line. So all of these vector B's are now tangent to the line. And so in this case, again, remembering that B dot ds is B, the magnitude of B, the magnitude of ds, cosine of the angle between them, and cosine of 0 is 1. So since cosine of 0 is 1, in this case, the integral of B dot ds will simply be B times the length of the line. So it'll just be equal to, in this case, we can make this just the integral of B times the integral of ds. So this will just be B times the integral of ds, and that will just be B times the length of the line. Now let's go ahead and apply this to Ampere's law and see if we can understand how this works. So if we have a current, let's picture over here, we have a current that is going into the screen. So if the current is going into the screen and we take our thumb, and do it with me, put your thumb into the screen, you'll see that your fingers will curl around in the clockwise direction in this case, and that will indicate the direction of the magnetic field. So that's what we're seeing here in this picture. So if we say that the integration path is a circle of radius r, we've drawn it right here, this is our integration path, and it will start and stop at the same point. So this point is both I and F. It's going all the way around to that same point. And here we know, as we just saw, that if we put our thumb into the screen and our fingers will curl around. So in this case, the magnetic field is everywhere tangent to the integration path. So it's going to be tangent to the integration path, and it has a constant magnitude. So in this case, we're considering a line integral of B evaluated along a circular path all the way around a wire carrying current I. So this is the line integral around what we call a closed curve. It's closed, right? We're going from one point, we're coming back to that same point. And so this is written with a circle around the integral sign. So it looks like this. When we have an integral with a circle right here, this circle symbol right here, that tells us that it is a closed integral. So it's going around, it's starting at one point and coming back to the same point. Now in this case, as we saw, B is tangent to the circle and is of constant magnitude at every point on the circle. So in that case, and we saw that when we have it completely tangent to the circle, then when we do the integral of B dot ds, the integral of B dot ds, that will just give us B times L. Well, L is the length that we're traveling on our path. So it's the length from point I to point F. And if we go all the way around a circle, we know that L all the way around a circle is just 2 pi r. And so if I take L equals 2 pi r and I put that in right here, I see that the closed integral is going to be B times 2 pi r. Well, we also know something about the magnetic field due to the Biot-Savart law. And the Biot-Savart law tells us that if we know that we have a current in a wire, and it's an infinitely long wire or a very, very long wire, then we can say that B is equal to mu naught I over 2 pi r. So in this case, we know that B is equal to mu naught I over 2 pi r. So if I put this in here for B, the 2 pi r's cancel. And in that case, and we see then that is where I is the current through the loop. So now that those two have canceled, we see that we can rewrite this. And the closed integral that is going all the way around, a closed integral all the way around our current of the magnetic field will be equal to mu naught times I. So This right here is Ampere's law. Now let's take it and expand it. That's one wire. That makes sense. It's the same thing we would get if we used Biot-Savart. It's not giving us anything too useful. But we can expand it. And so we see that even when we have our path, as long as it is a closed path, it can be any shape. So as long as it is a closed curve, the integration path is a closed curve, as long as it's closed. Then in that case, whenever the total current I through passes through an area bounded by a closed curve, as long as it's closed, the line integral of the magnetic field around the curve will be given by Ampere's law. And that will be what we just saw. The closed integral of B dot ds is equal to mu naught times I through, whatever is going through that closed curve. So the currents, as we see in this schematic right here, this drawing right here, there are currents that pass through the bounded area. That would be current I2 passes through the bounded area, current I4 passes through the bounded area, and current I3 goes through the bounded area in the opposite direction. So we know that if we add up I2 and I4 and subtract I3, that is the total current I through. That is what this is right here, I through. And if we multiply that by mu naught, just the constant mu naught, that will give us the integral of the magnetic field around that curve. So that is Ampere's law. And as long as we have a closed curve, we can use symmetry to find out what the magnetic field is around the curve, or vice versa. If we know the magnetic field, we can use that to find the current going through our closed curve. All right, let's now look at a practical example, that of a solenoid. So this is an image of a solenoid, and we see that it is basically, it's a helical coil of wire with the same current I passing through each loop of the coil. So here we see the current I going in over here on the right and coming out on the left, the way this one is drawn, and it's going through each of these coils. So each of these coils, the current is going through the coil. And so each of those coils has the same current I going through each coil. Solenoids may have hundreds or thousands of coils. They're often called turns, so it might be written as a turn instead of a coil. And they're sometimes wrapped in several layers as well. The reason that solenoids are so valuable is because we can create a uniform magnetic field with a solenoid. So a solenoid can give us a uniform magnetic field, and that is very valuable. Let's see what that would look like. So here we have a solenoid, and on the white paper behind it, there were iron filings, and those iron filings were there before we had any sort of current going through our solenoid. And before there was any current, those iron filings were dispersed however which way. But once we turn on the current through the solenoid, we see how these iron filings line up, and those indicate the magnetic field. And so we can see that the magnetic field lines are very close together and uniform in the center of our solenoid. So the magnetic field is strongest and most uniform inside the solenoid. So it's the strongest and the most uniform inside the solenoid. Let's look specifically at the magnetic field of that solenoid. So with many current loops along the same axis, the field in the center is strong and roughly parallel to the axis, whereas the field outside the loops is very close to zero. So here is just a single loop. And here the magnetic vector is shown here at 6 different points. So we see different points here. And now, instead of just having a single loop, now we have a stack of 3 loops. And here, right, we can see that when we have those 3 loops, right here at this point, the magnetic field will basically cancel just with these 3 loops here. So when we have a solenoid, we can have the magnetic field, we can assume that that's pretty much zero right outside of our solenoid. Now, inside the solenoid, we see that all the magnetic fields inside the solenoid will all point in the same direction, and they will all be horizontal and in the same direction. And so the fields inside the solenoid reinforce each other. So that's if we have 3 loops, it's just 3 loops. Now, if we then expand that to a solenoid, we see that for a solenoid, the magnetic field outside the solenoid is 0. And the magnetic field inside the solenoid is uniform, and especially along an infinitely long solenoid. And even if it's not infinitely long, as long as it's much longer than it is wide, then we can consider that it is an infinitely long solenoid. And the magnetic field outside the solenoid is 0. So outside the solenoid it's 0, and inside it's uniform. So that's why it's a very useful solenoid. So again, no real solenoid is ideal, but a very uniform magnetic field can be produced near the center of a tightly wound solenoid whose length is much greater, much larger than its diameter. Now, this figure shows a cross-section through an infinitely long solenoid. So here is our solenoid. It's infinitely long. We're just seeing a piece of it. And what we're going to do is have an integration path that we'll use, and to integrate across to find, to use Ampere's law, we'll have an integration path. And that integration path will be this rectangle right here, this black rectangle that I'm tracing over right now. And so the current that is passing through the rectangle, the current that's passing through will be just this current that's coming out here. And that will be N, the number of loops that is going through the rectangle, times I, the current. So it'll be N times I will be the current through the rectangle. And here, B at the is tangent to the integration path along the bottom edge. So along the bottom edge, B is tangent to the integration path. So it'll just be B times L. And outside, along the top of our integration path, there is no field out there. So since the magnetic field is 0, that would just be 0. And B will be completely perpendicular to the sides. And so in that case, it will be 0 there as well. So Ampere's law, we know, tells us that the integral of B dot ds is mu naught times I through. So in that case, the integral of B dot ds in this case equals BL, and that equals mu naught Ni, because we see that Ni is what our I through is. Now along the top, here, along the top, the line integral is 0, since B equals 0 outside the solenoid. So we know that B equals 0 outside the solenoid. Now along the sides, the line integral is 0, since the field is perpendicular to the path. So here we see that it's perpendicular in any place where the magnetic field is perpendicular to the path, the line integral will be 0. Along the bottom, the line integral will simply be B times L, because it is completely parallel to the path. So it will be just B times L. Now, if we solve for B inside the solenoid, we see that the B solenoid is going to be mu naught N times I over L, and that equals mu naught little n times I, where little n is going to be equal to N over L, where N over L is the number of turns per unit length. So it's like a density of our number of turns. So let's look a little more closely at the magnetic field outside a solenoid. The magnetic field outside a solenoid looks a lot like that of a bar magnet. So here's outside our solenoid what's going on. And over here, we see what a bar magnet would look like. So we see that in this case, a solenoid is just an electromagnet. And in that case, we can use our right-hand rule So we take our fingers and point them in the direction that the current is going. So if I curl my fingers around it, the direction the current is going, my thumb will then point to the North Pole end. So it'll point to the North Pole because the magnetic field will go out to the North Pole and it will come in the South Pole, just like it does for a magnet. So that's how we can see what our magnetic field is outside our solenoid. All right, so we have used Ampere's law, which told us that if we have a closed curve, that if we then do the line integral around a closed curve, that will, of the magnetic field around a closed curve, that will give us mu naught times the current through that closed curve. And then we looked at a specific example of solenoids, which are very useful because if we have a solenoid, we can have a uniform magnetic field inside our solenoid and zero magnetic field outside our solenoid.